All right, so this is the mixed 6 activity that you did today. So the mixed 6 is going to be focused on just a couple of skills, but it's going to hit this skill from all different directions. So we have something very straightforward, like recall a fact, carry out a procedure. Then we get into a little bit trickier when we talk about classifying a mathematical object into some sort of category. Proving, explaining, justifying, then we take this concept and extend it a step further. And then we also want to look at some error analysis. So this gives you like a well-rounded view of just kind of a focused bit of a topic, okay? So I'm going to post this answer key, but I also wanted to give you a little bit of explanation if you needed it. So if you're watching this, I'm going to kind of talk through the answers. Feel free to fast forward and jump around to just the pieces that you maybe weren't super confident on. So number 1, factual recall. We have this polynomial function p of x, and we just want to identify these characteristics. So P of x has a leading coefficient of 5, a degree of 4, and then the leading term is that 5x to the 4th. So the degree of this polynomial is the highest degree, which it is in standard form. So for us, that is first. So the degree is 4. The leading coefficient comes from that same term. It is going to be positive 5. And then the constant term is the one without a variable on it. So that is negative 2, okay? D says a 0 of the polynomial function p if x minus 2 is a linear factor of p. Well, remember, if x minus 2 is a factor, then to find the 0, we would set that equal to 0. So that would mean that x equals 2 is a 0 of this function as long as x minus 2 is one of the factors, okay? So that's a little bit wordy there, but that's what it is saying. Identify a 0 if I know that x minus 2 is a factor. So that would be x equals 2. All right, carry out a procedure. For this polynomial function g of x, we want to find the zeros and their corresponding multiplicities. So again, for the zeros, we're going to set each factor equal to 0. Now look at what you wrote down on your page, because if all you have written down is a number, that is not how we want to write this. That again is called a bald answer. These are x values, so we need to label them as such. So make that note to yourself. That is something I will expect to see on your test, okay? So x equals negative 3 is a 0, x equals negative 1 is a 0, and x equals positive 4 is a 0. Now, the multiplicity is based on the factor that came from. It's how many times is that 0 or that root repeated. So that's going to come based off of these exponents here. So x equals negative 3 has a multiplicity of 3. X equals negative 1 has a multiplicity of 2. And x equals 4 has a multiplicity of 4. So then that information helps us answer B, which says at which of these zeros is the graph of the polynomial tangent to the x-axis? Now remember, this phrasing means it just touches it but turns around. This is what's happening when we have a bounce on the graph. At a 0, it's going to go towards it, just touch it at that one spot, but then carry on still on the same side of the axis. And we know that that happens whenever we have an even multiplicity. So that is going to be these two places. And the zeros where that happens is at x equals negative 1 and x equals 4. All right. Number 3, classify a mathematical object. So we want to classify each of these as even, odd, or neither. Now, remember that if this is multiple choice, you can certainly look at it in your head however you want to. If it is free response, the test is going to be that you need to show that you have evaluated f of negative x, or in this case, they're called P1, 2, and 3. So P1 of negative x is the first thing that I need to find. And so if this is a free response question, I want to see that you are plugging in negative x for all of the x's. So we have 5 times negative x to the 4th plus 3 times negative x squared minus 4. Now, when I square or fourth power these negative x's, because these are even exponents, they're all going to become positive. So this will stay positive 5x to the fourth plus 3x squared. And the constant, by definition, will stay constant. So it's just still minus 4. Since every single sign and every single term stayed exactly the same, that makes this one even. Now, again, you can tell by looking at the powers. Even power, constant. Those are not going to change signs. So if this was multiple choice, you can just kind of eyeball that. So let's think about the second polynomial in that way as if this was multiple choice. Even power, gonna stay the same. Even power, gonna stay the same. But 2 times negative x, that's gonna change this to negative x when I plug in. So only one of my 3 terms flipped signs. It has to be all or none. So since this is a mix, then that means this is neither even nor odd. If I look at P3, I have odd power. That sign is going to change. Again, x to the first, odd power, that sign is going to change. So P3 of negative x, when I plug this in, I would end up getting negative 6x cubed minus 2x. Every single sign became opposite on that one. Odd, opposite, origin, all the O's. That one is going to be odd. All right, if I look at this graph in number 4, this appears to be symmetric over the y-axis, which means that this has y-axis symmetry, which means it's even. And if I look at this one, this does appear to have origin symmetry. It's kind of hard to tell what the values are, but if this is like positive 0.5, positive 1.5, then this point would be negative 0.5, negative 1.5, and that is what tells us that it's odd. Every AB becomes opposite A, opposite B. So there are our evens and odds. All right, number 4, prove, show, or justify. For each of the polynomial functions, write appropriate limits to describe the end behavior and give a reason for your answer. Okay, I'm going to shrink this pen down and see if it fits a little bit better because I'm writing pretty small. Alrighty, so the first one, f of x equals 5x to the fourth plus 3x squared minus 4. The leading term is 5x to the fourth. So that means that I have a positive leading coefficient and I have an even degree, okay? Even degree and even symmetry is not the same thing, remember, so make sure you study the difference between those. But an even degree, so first we look at the positive leading coefficient. That tells me that my right arrow is going to go up. And then the even degree tells me that my left arrow, just kidding, is going to go the exact same direction. So up is what we want. So our limits, the limit on the left arrow would look like the limit as x approaches negative infinity, because that's the left side, of our function, which is called f of x, equals, since my left arrow is going up, that means we are going towards positive infinity. Then the right arrow limit will be very similar, except my x's are approaching positive infinity of f of x equals. My right arrow is also going up, so it goes to positive infinity. So again, negative infinity to infinity, that is our right arrow. The other one is, that is our left arrow. The other one is our right arrow. And the reason, I really should have put this here, the reason is this. We have a positive leading coefficient and an even degree. Okay, so on B, again, the leading term is the first one in this case. It is in standard form. I have a negative leading coefficient and I have an odd degree. So that tells me that my arrows are going to be right arrow is down because my leading coefficient is negative. And then since it's odd, my left arrow has to go in the opposite direction. So left arrow up will say the limit as x approaches negative infinity of, this one is called h of x, equals, left arrow is up, so that goes towards positive infinity. Other side, the limit as x approaches positive infinity of h of x equals, the right side is down, so our y's are going towards negative infinity. Okay? All right, number 5 does require a graphing calculator. Let me grab mine here. All right, so it says the figure shown is the graph of a polynomial function m. Write an expression for m in factored form using a as the leading coefficient. So we don't know what the leading coefficient is, but in factored form, I should have 3 zeros. X equals -2 is a 0, x equals 0 is one of our zeros, and x equals 3 is one of our zeros. That tells me, now they told us this function is m of x. It's named m, so I'm going to say m of x equals a times, that's our leading coefficient. Now I'm going to write all my factors. Now because I know what the zeros are, I know that x plus 2 would give me a 0 of -2. And I also see that the graph bounces there. So that has to have an even degree. And remember, the higher the multiplicity, the flatter the graph gets. And this doesn't look very flat right there. So I'm just going to go with squared as my smallest even multiplicity. And again, that's because I see it bounces. Then at x equals 0 and at x equals 3, I see it crosses right through. So those are each going to have a multiplicity of 1. So x is how I get 0, and then x minus 3 is, can you hear my cat? Is how I'm going to have a 0 of positive 3. Now, I don't love the way this is written because typically if we just have a monomial factor, we put it in the front. So if I was going to write this in a way that I liked a little bit better, I would move that x to be up here. Whoops. Ax times x plus 2 squared times x minus 3. That's more likely what you would see in multiple choice or something like that. We always put the monomial factor first. Okay, we did not need a graphing calculator for that. But now for B, it says which value of A in the list below displays a polynomial that best matches the graph of M. Now, we can make some decisions here first without having to put anything in our calculator. Look at our end behavior. I know my end behavior is down on both sides. So that tells me my leading coefficient has to be negative, so it cannot be these two. The question is it negative 0.2 or negative 0.3? Now, what you want to look at in your calculator is you're going to graph both of those and put in those two A values. Your x's will stay the same. The rest of the equation will look the same. And we are looking for the one that has a maximum like close to 6 here, and maybe this relative minimum close to -1. That's kind of what I would be checking. So let me pause this and I'm going to pull up Desmos here so I can show you on the screen. Now you can use your graphing calculator for this, but let me kind of show you what this is going to look like. I'll be back in just a second. All right, so you can't do this in your graphing calculator, but I've got this set up where I can change the value of A here to whatever I want to. So we can see that if my A value is positive, my arrows are going to be going up on either side. So I don't want that. If my A values are negative, both sides are going down. That's good. So let's put this at negative 0.3. So this minimum here looks maybe close to about -1, but the maximum is clear up here you can't see the thing I'm pointing at. I don't know why that's not showing up on your screen. But anyways, the maximum is close to positive 10. That seems too high. So let's change it to negative 0.2. And we can see that's kind of close to 6 for that relative maximum and kind of close to negative 1 for our relative minimum. So I would definitely say that negative 0.2 is the one that we want to have. So negative 0.2 is probably the A value that works with that the best. Okay, now number 6, critique a fallacy. So there's something wrong here that we're trying to identify. Fallacy is something that is false. So it says, Sophie attempts to find the zeros of the polynomial function q of x. Sophie graphs the function on her calculator and states that the function has exactly 2 complex zeros. Explain what is wrong with Sophie's statement. Write a correct statement about the complex zeros. Okay, so we are going to go to the graphing calculator again. So you'll want to put this in your Y1 and then go ahead and graph it. I'm going to pull this up on Desmos again. Ta-da, here's the graph. Okay, so what I see here is that I have 2 places where I cross the x-axis, okay? But I also know that the degree of this function is 4. And that fundamental theorem of algebra that is in your notes says that we will have the same number of complex zeros as the degree of our function. So saying that it has exactly 2 cannot be correct because each of these zeros here and here crosses. Oh, hold on. Okay, if you could hear that in the background, that's my cat's automatic feeder calling them to come have their lunch. So anyways, this graph crosses at both of these spaces. This one pretty clearly has a multiple of 1 because it goes straight through like a line. This other one over here does look like it starts to flatten out a little bit, but it still crosses pretty straight. It flattens out kind of around this area. Just for a second, it slows down. If this was going to be a multiplicity of 3, maybe it might flatten out a little more like that. But even still, this is either going to be 3 and 1, or it's going to be 1 and 1. And so that means that I either have a 3 and 1 multiplicity, which is possible, or that I have a 1 and 1 multiplicity with 2 that have imaginary parts, okay? Remember that complex numbers, you talked about this in Algebra 2, but if you need a refresher, complex numbers are anything in the form a plus bi. Now, complex numbers do not have to have an imaginary piece. They do not have to have a real number piece. If a is equal to 0, then we just get bi. That's called a pure imaginary number. It doesn't have the real number part. If b is equal to 0, then I just have a, which in this case is just a real number. Real numbers are a subset of the complex numbers. So we've talked about like integers, whole numbers, okay? Whole numbers, integers are more than that. If I add in fractions, I get rational numbers, okay? The irrational numbers are out here. And this whole box here is our real, numbers. But then there's another ring outside of this that has our complex numbers. So real numbers are a part of the complex numbers. They are going to be in there. And so even though we may not get imaginary zeros, real numbers count as complex zeros. So again, the real reason why it cannot just be 2 is because my degree is 4. So if we go back to what she said here, She graphs the function on her calculator and says that the function has exactly 2 complex zeros. We can see why she thought that, because it crossed the x-axis twice. But so the reason why it cannot be, you should have some answer that talks about the degree. Since the degree is 4, that's going to mean that there are 4 complex zeros. So she's short by 2, and that's why that last one is what it is, okay? So that's a good kind of look at those last 2 sections, 1.5 and 1.6 that we talked about. So definitely make sure that you understand these 6 questions. Good luck on your test.